Hi everyone. So in this lecture we're going to start one of the last topics that we're going to cover in this course, which is counting. Now I know that that sounds kind of silly on the surface, but what we're going to be counting here are things that are that could in general be more complicated to count. You might be asked to figure out how large is a collection that satisfies some restrictions, and then it quickly can become a non-trivial problem. In fact, there's an entire area of mathematics devoted to this called enumerative combinatorics. So we're kind of getting into the basics here, and for those of you that are going to go on to other courses, this will actually help you in several different future courses, such as maybe probability and statistics, but also if you do want to take one of the follow-up courses, which would be combinatorics, you would definitely use it there, as well as many other areas. Okay, so one of the first things that I wanted to talk about is the product rule. So here, when you're counting things, here's sort of what the product rule says. So suppose that a procedure can be broken down into k tasks, and if there are n sub I ways to do the ith task, then the total number of ways the procedure can be done is the product of n1 times n2 times n3 all the way up to nk for your k tasks. So you can kind of think of this as they're independently done, or things are independent in a way. Okay, so let's look at an example where you could use this. So how many ways can a president and vice president be chosen from a group of 30 people? Okay, so if I give you a group of 30 people, you're going to have to make a choice for, number of choices for, so there are 30 choices, number of choices for the president in that group. Okay, and then how many can you choose for the vice president? So this is an example where you can use the product rule because you're kind of breaking it down into these two tasks here, right? So I have 30 choices for president, but when I choose the vice president, it would have to be someone different, right? So there's going to be 29 choices for this. So number of choices for vice president. Okay, this is of course assuming that you couldn't fulfill both roles, which I think is a reasonable assumption, right? So of course you could actually calculate this number, but for a lot of these problems, I'm actually going to leave the answer in sort of an expanded form, whether it involves multiplication or addition, because it actually reveals how you actually calculated this. Okay, so let's leave it as that. So that would be the total number of ways that you could do this. Okay. All right, so second example, how many different 7-digit telephone numbers can be made with the only restriction that the first digit cannot be a 0? Okay, so you're going to have 7 digits. Okay, and you're going to make some choices, right? So the very first one, the very first digit, that's the only one that actually has this additional restriction, right? So it cannot be 0. Okay, so how many choices? So how many choices for digits? There would be 9 choices, right? It can be 1 through 9, but it can't be 0. So there'll be 9 choices for this. And then the second one is independently chosen, except so are there any other restrictions? So you can make 7-digit telephone numbers, and you're allowed to have repeats, right, for the second digit. And actually you have even more choices here for the second digit, because that one doesn't have the additional restriction that it can't be 0, right? So I'm going to have 10 choices for the second digit, 10 choices for the third, fourth, fifth, sixth, seventh, right? So choices, 10 choices for all other digits. Okay, so this would be total. Okay, what if we add the restriction that no digits can be repeated? So kind of using the same procedure. Okay, so 3, 4, 5, 6, 7. Okay, so we still would have this additional assumption that the first one cannot be 0, so there'll be 9 choices. 9 choices, right? Since it cannot be 0. Okay, so I have 9 choices for this. And then, you know, up here I should have written all these as product up here. Okay, so for the second one, this additional restriction that you can't have repeats would actually reduce the number, right? So instead of 10, I'm actually going to have 9 choices here. So 9 choices for the second digit, since it cannot, whatever digit we actually chose for that first one, it cannot be that. So we'd have to exclude that possible digit, but then you'd have 9 remaining possible digits for the second one. And then you go to the third one, and how many would you have here? Well, the only restriction for this third digit is it can't be the same as the first two, whatever the first digit was and the second digit. So there'll only be 8 choices for that one, and then there'd be 7 choices for the next one, 6, and then 5, and then 4. Okay, so it would be this many. Okay, so I think this is a good example to point out. This is definitely something a little bit non-trivial to count how many total things satisfy this condition that's like a non-trivial condition. It's not super hard to calculate it, but this is an example where enumerative combinatorics can start to lead to some more complex problems. Okay. Okay. How many functions from a set of m elements to a set of n elements are there? All right, so I think to help answer this question, it might be a good idea to actually draw like a diagram here. So let's say you have your domain set A, and let's label some of these elements. Okay, so I have A1, A2, A3, A4, and what do we know? The size of A, right, is you're going from a set of m elements to a set of n elements. So this will be A sum m, and then over here we're going to go to, so the size of A is m, and you're going to go to a set of n elements. Okay, so the size of B is going to be n. So let's label some of these. So this would be B1, B2, B3, B4, all the way to Bn. Okay, and now you're going to create some function, right? So the restrictions are what? Well, the definition of a function, right? So we have to think about that. So how many functions are there? Well, the restrictions, so let's just think about this element-wise. So to be a function, I have to have that every element of the domain has to get mapped somewhere, right? So this has to go somewhere. So f of A1, how many choices do I have for this? Has n possible outputs, right? This could be B1, B2, B3, B4, all the way up to Bn, right? Okay, so once you pick it though, okay, so once I pick it, does that change what f of A2 can be? Well, a function just says that every element of the domain has to get mapped to something in the codomain. It doesn't restrict it from being the same as what the previous one was, right? Because, for example, that would have been like adding an additional condition that it's a one-to-one function, but that's not here, right? It just says how many functions do I have? Okay, so f is going to be a function from A to B, and we want to know how many such f's are there. Okay, so coming back here, so f of A1 has n possible outputs, and f of A2 has n possible outputs, right? Because I'm allowed to repeat outputs, right? For example, I could have a function where every single one of these maps to B1, right? That's a legitimate function, so that's got to be one of the possibilities, and so on. And do you see that you have f of AM has n possible outputs? Okay, so that right there gives you an idea of how to calculate this, right? So the total number of functions would be equal to what? Well, I have n choices. We said we had n possible outputs, so I have n choices for the first element, and then I have n choices for the second element, third element, fourth element, all the way up to the mth element, right? So choices for mth element, which we called it AM, right? The first element was A1, and this one is AM. Okay, so how many things do I have here, right? So this is M times. So I actually have n to the m. So if n and m are large, there's going to be quite a lot of functions, right? If n and m are small, then this could be very few, right? Okay, now what if we ask the same question, but we add an additional restriction here? So how many one-to-one functions from a set of m elements to a set of n elements are there? Okay, so kind of looking at this picture again, I'm going to have kind of the same thing, but let me kind of draw this a little bit. You'll see that this additional restriction here will give you kind of, okay, so let's, okay, so I have A1, A2, A3, and then dot, 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 all the way up to AN, right? Is it AN? Oh, sorry, AM. And B1, B2, B3, up to BN. Okay, now if you're requiring that the function is also one-to-one, then your functions have to look something like this, right? So let's say that the very first element goes to B1, right? So this would be like f of A1, could be that. What about f of A2? Well, in the previous example, I'm allowed to have the inputs, I'm allowed to have outputs repeat, right? So I could have a distinct input go to the same output as the first one. So for example, I could have A2 go to this same output in example 3. But here I'm requiring that the function is one-to-one, which is an additional restriction, right? So this actually means that that A2 can't go to that first one, right? It has to go to, since these two are distinct, it has to have a distinct output. So this would be like your f of A2, right? So here's kind of an example, right? Here's what the picture would look like, okay? At first. Okay, but let's backtrack a little bit. Okay, so let's take some of this away, because things are general right now, right? So here's our f, right? And so f of A1 has n possible outputs, right? Could be any of these. Okay. Now f of A2 has n minus 1 possible outputs, because it cannot be the same as f of A2, or sorry, f of A1, because f is a one-to-one function, right? Since f is required to be one-to-one, okay? And then same thing, f of A3, continuing this, would have n minus 2 possible outputs, right? And the reasoning for that would be because it cannot be the same as f of A1, and it cannot be the same as f of A2, whatever that is, right? And so on, right? I don't want to draw them in because it would give a specific example, okay? And then you keep going, and here we actually might run into a problem, right? Because you'll eventually get to the very last one over here. F of AM has how many possible choices here? Well, it would be n minus m minus 1 possible choices, or possible outputs, right? as long as this is, as long as this is greater than or equal to 1, right? Because if you don't have any choices, if this last guy, do you see that there could be a problem here? Because if there aren't enough possible outputs, then this might not be able to go anywhere, right? So if this can't have a target and avoid repeating one of these previous outputs, then it would no longer be a one-to-one function, right? So we actually have kind of a restriction here, right? So let me just show you an example of what I'm talking about real quick over here. So if I had a set like this and a set like this, so let's say A had 3 things and B had 2 things, right? So I could have the first element go to the first one, second element go to the second one, and then this one has no possible output and remain one-to-one. Do you guys see that? So you would have three elements of the domain, and if you're just requiring it to be a function, of course this could have either of those as an output. But once you additionally require that the function is one-to-one, then I have to make sure that this distinct element does not repeat one of the already chosen outputs, right? I actually have to be a little bit careful with my choice here. So I guess what you could say is this: if m is strictly greater than n, if the size of the domain is bigger than the size of the codomain, then there are zero or none, no one-to-one functions, right? There are no one-to-one functions, okay? But what happens if it's less than or equal to? If m is less than or equal to n, then I can use the work up here, right? So then it would look something like this. I would have, here's A and here's B. Okay, so let's say I have 2 things in A and 3 things in B. So this first one, I could pick one of these 3 choices, and the second element, I could pick one of the remaining 2 choices. Then there are, so it would be n times n minus 1 times n minus 2 times dot 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 all the way to n minus m minus 1 total one-to-one functions, right? So that's just multiplying all these possible output choices here that we had before. Right, so we had n for the first one, n minus 1, n minus 2, and then so on and so forth until you get to the last one, and we'll have n minus, in parentheses, m minus 1 total. Okay, so this is definitely an example of something that's non-trivial when you carefully look at this, right? So this is a really good example of a question from enumerative combinatorics, and these show up all over the place. You can have lots of situations where you're asked, okay, I have a collection that has to satisfy these conditions, right? I have these rules that have to be followed. How many ways can you configure this thing to follow those rules? This comes up all the time in computer science, physics, chemistry, lots of applications. This comes up everywhere. Okay, so all right. Next question, how many bit strings are there of length 10? So what is a bit string? Well, bit string is an array or just sort of like a phone number. You could say has 7 digits. A bit string is just you have zeros or ones, and it's an array or string, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so bit, it can be 0 or 1, and strings, these are just arrays. So you could just think of it as a list or sequence. List or sequence or array of bits which are 0 or 1. Okay? Okay, so I'm allowed to put 0 or 1 in any of these positions, and there's 10 total. So how many do I have for the first one? I have 2 choices, right? I have 0 or 1. So that's 2. And then same thing, I still have 2 choices for the second, the third, the fourth, and so on, right? All the way up to this last one. There's no restrictions the way that I'm writing this. Okay, so what would that be then? Well, it's just 2 times 2 times 2 times 2, a total of 10 times. Okay, so the length here is how long the sequence is, like how many places do you actually have there. Length of 0, we would just call that like an empty bit string. Length 1, it would just be 0 or a 1. So this would be 2 to the 10. So just some examples. An example. So here's a bit string of length 3. Okay, so you could have 1, 0, 1, right? That's length 3. So length 3 is small enough that you could actually list all of them. What are all the bit strings of length 3? Well, you could have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and then 1, 1, 1. So there should be, just kind of generalizing so the total, it should be 2 to the length, right? Which is 8. And there are 8 here, right? 1, 2, 3, 4, 5, 6, 7, 8. And in fact, these are actually the listing of the numbers from 0 up to 8 in binary, actually. So maybe you're familiar with that. So it's just another way of writing out numbers in a different base, right? The numbers you're used to are written in base 10. This would be written in base 2, where you only have 2 digits to work with, 0 or 1. Okay, another common rule, other than that product one that we had up above, is called the sum rule. So suppose that a task can be done in one of n1 ways, or of n2 ways, or so on and so forth, nk ways. So when you kind of are separating these tasks with ors, okay, then the total number of ways that the procedure can be done would be the sum of all of those. So n1 plus n2 plus n3, so on and so forth, up to plus nk. Okay, so how many ways can a single digit or a lowercase letter be chosen? So, I mean, you got to put some context into this, but by digit, right, we mean this can be any number, any integer, 0 to 9 inclusive. So there are 10 choices, right? Okay, and then lowercase letter. Now, if we're talking about using, English here instead of something like, the Cyrillic alphabet or something like that, then there's 26 choices, right? 26 total choices. Okay. Now, how many ways can you choose this or this? The or there is telling us to use the sum rule. So this would be 10 plus 26, which is 36. Okay, so how many ways can you choose? One or the other. Okay. Here's a good example. So how many bit strings are there of length 6 or less? So if I just asked how many of length 6 there are, we actually already know that, right? So that would be 2 to the 6th, right? This would be the number of bit strings of length 6, right? Just adopting our previous idea. If it was length 10, it would be 2 to the 10, right? Because you have 0, 1 choice for each of these and so forth. But I'm saying or less. So that means you could have length 5, 4, 3, 2, 1, or 0. So since I'm adding this or in here, you're going to add up all of those. So it'd be plus 2 to the 5th, plus 2 to the 4th, plus 2 cubed, plus 2 squared, plus 2 to the 1 plus 2 to the 0. So this one right here would be the number of empty bit strings, empty bit strings. So it's just, there's nothing there, right? So it's empty, okay? There's one way to do that, 2 to the 1. Now, this is the number of bit strings of length 1. There's only 2 of those. That's 0 or 1, right? So 1 or 0. Those are the 2 that are length 1. And then of length 2, there's 4 total, right? Length 2. I could list all those out, right? 0, 0, 0, 1, 1, 0, and then 1, 1. So there are the 4. And then the length 3 ones, right? We just listed those actually out as a secondary example to this one, right? So there were 8 of those, and so on. Okay, so how many of length 6 or less, right? So here's where we can use that sum rule. So this would be the total. I mean, you could calculate all of these things, and you could calculate this actual number, and it depends on the problem. If you're going to use that problem for something else, it's probably a good idea to actually figure out what that number is. But in a lot of cases, I would prefer like the expanded version of this, so I can actually see how you're arguing this, right? So like this would be very clear to me. You know, you're indicating what you're doing here, how you calculated it. Okay. Now, before, I actually did show you the inclusion-exclusion principle for sets. So when we were learning about sets, union, intersection, and cardinality, I mentioned the inclusion-exclusion principle, and it's actually quite useful in enumerative combinatorics. So suppose that a task can be done in one of n1 ways or in one of n2 ways, but some of these ways overlap with one another. So how do you count the total number of ways to do the actual task? So the key to this would be to use that inclusion-exclusion principle that we know from sets, that the size of the union would be the size of A plus the size of B, the cardinality when I'm saying size, right? So the cardinality of the union would be the cardinality of A plus the cardinality of B minus the cardinality of the intersection. So if you kind of go back to the original picture that we actually had here, maybe I could draw that for you. So you kind of have a universe, and you have a set A and a set B. Okay, and if you're trying to figure out how much stuff is in this union, right, if you just add up how much is in A to how much is in B, you actually counted this intersection twice. You see that intersection gets counted twice. If I add up how much is in A and then how much is in B, you see that intersection is counted twice, so that's why we have to subtract it off. So it's quite useful. Now, if the sets are disjoint, then the intersection is empty, and you really just have the sum of them. So when things are disjoint from each other, it's very easy to count them. Okay, but we're looking at situations where you do have overlap, so it's going to be more complicated to count these things. So here's kind of an example to illustrate that. So suppose that we have 50 people take a survey. 20 people report that they have at least one dog, 25 people report that they have at least one cat, and 16 people say that they have both. Okay, how many people taking this survey have neither a cat nor a dog, right? Probably should say nor there, right? Okay. Okay, so let's think about this in terms of sets. So T would be the set of all people. This is like your universe. Your universe. And we know the size of T is 50. So 50 people are taking the survey. Set of all people taking the survey. Okay, so we have this universal set. 20 people say that they have at least one dog. Let's call that D. So this is set of people. Whoa. I don't know what just happened there. Okay, sorry, I had a small glitch there. So so D, let's say that it's a set of people that have at least one dog. So greater than or equal to one dog. Okay, and then 25 people. Oh, sorry, what do we know? We know the cardinality of this set. So the number of people that say they have at least one dog was 20. Okay, and then we also have 25 people report that they have at least one cat. So let's call that C. So the set of people that have greater than or equal to one cat. So we know that the size of this set is 25, but there's some overlap here, right? So it says 16 people say that they have both. So that would be the intersection, right? So if you take D intersect C, this would be the set of people that have so set of people with greater than or equal to one dog and set of people with greater than or equal to one cat. Okay, and we know how big this is, right? So the number of people in this set, which is the overlap, is what? So that's 16. All right, so this is kind of useful information. I'm just assigning set names here to kind of help illustrate this. Then the question is, how many people taking the survey have neither a cat nor a dog? Okay, well, if you kind of draw a picture for the situation that we're in, right, similar to what we had before, you have sort of the universe of people taking the survey, you have your dog people, you have your cat people, and then you have this intersection here of the cat and dog people. And then outside of this set, you know what, let me write it like this actually. So here's D, and here's C. And then outside of this would be the people that have neither a cat nor a dog, right? So this would be, we need to find how many people are in the red. You know what, let me actually label it in red. In the red. Okay, so someone in this set, so this would be people that took the survey in T, that took the survey that are not in the union of these, right? Is in one or the other. Okay, not in that union. So what we could do is we can use this inclusion-exclusion principle to actually figure out how big that union actually is, right? So by the inclusion-exclusion principle, so first of all, D union C would be set of people that have greater than or equal to one dog, or set of people with greater than or equal to one cat, right? So how big would this be? Well, according to the inclusion-exclusion principle, this would be the size of D plus the size of C minus the size of this intersection, right? So we actually have all of those numbers right here, right? So this would be 20 plus 25 minus 16. Right, so 45 minus 16 is 29. So there are 29 people in this union, and then how many people are outside of that, right, in the red? So in the red, let me switch colors here. So the red set, which is actually T minus this union, right? So it actually would be the set deletion. If you took the universe and you took out the stuff in that union, okay, so the size of the red set is actually the size of this. Okay, that would be the total number that took the survey minus the size of this union that we just calculated actually, right? So how many people took the survey is 50. Okay, so 50 people took that survey, but 29 of them were in one of those two categories, right? They either had a dog or they had a cat. Okay, so then that leaves 21 left. So those 21 people have neither a cat nor a dog, right? Okay, so that's kind of an interesting problem where you can use some more complicated techniques such as the inclusion-exclusion principle to calculate this for us. So that's kind of a neat problem. Okay, now when we actually learn the inclusion-exclusion principle, I did give you an example that's very similar to what we're going to do right here, but I think it's good to revisit this. So let's say that let's just build a universe to begin with. So how many positive integers less than 400 are there? Okay, so first, let's actually just give that set a name. Let's call that U, because I'm going to use this later on, and it'll be the universe. So this is the set of positive numbers, right? That's positive integers. The set of positive integers was denoted in this way, right? Such that n is less than 400. So let's, if I said less than or equal to, we would include it, but the way that it's written, less than, it should be strictly less than that, right? So now if you want to, so this is using set builder notation, but using it in a roster form or list form, it would look like this, right? So dot, 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 up to 399. Okay, first question is how many positive integers less than 400 are even? Okay, so I could write that out, right? You could call it E. We actually did have a notation for this, which is 2z. So you're kind of taking the integers, multiplying all of them by 2. You'll get the evens. Okay, but with this set, that would be all evens, right? But here we're specifically restricting ourselves to be positive integers less than 400. So instead of writing that, what you're going to do is, well, you could use your set builder notation. You could say this will be, they've got to be, you know what, let me call them n's again. So n will be in this universe. Okay, so it's got to be something less than 400, but positive, and n is even. Okay, now if you want, you could write that again. N being even, you could simplify it a little bit. Now the definition would mean that it's 2k for some integer k, and well, I don't have to add an additional restriction because I'm pulling n from this universe, which I already know is positive and less than 400. If I had written z here instead, integers, then you would have to add that additional restriction here. Okay, so this would be a good way to write it in set builder notation in roster form. So first of all, we actually just wrote the sets, but we didn't answer how many are there, right? So how big was this actual universe? That is 399, right? I mean, you could see them listed here, 1, 2, 3, all the way up to 399. So there's a total of 399 of them in that set, right? What about the evens? So if I list this out, I'll have 2, 4, 6, 8, blah, 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 all the way up to 398, right? Okay, but how many are there? So how many are in this set? So how many evens are there? Well, one way that you could manipulate this a little bit is you could rewrite it so it's a little easier to count. And one way that the reason this first set was easier to count is you can just see them right there, right? It goes 1, 2, 3, dot, dot, dot to 399. So clearly there's 399 of them there. Here it's a little bit, I mean, it's not crazy hard, but you see if you stare at it a little bit, I could write this as 2 times 1. I could write this as 2 times 2. 2 times 3, 2 times 4, and then you keep going, and then 398 is 2 times 199. Okay, now if you look at this second factor here, let me just write this in another color here. So if you look at the second factor, right, it's a little easier to count them now. Do you see that it goes 1, 2, 3, 4, all the way up to 199? So this total is 199. There's 199 even numbers that are positive and less than 400. Okay, how many are divisible by 4? So let's try the same exact thing. Let's call that a name. Let's figure out what that set would be. So you could do it in set builder notation, but let's just try to list it out. Okay, so divisible by 4, it would have to be, right, we're talking about multiples of 4 here. So you have 4, 8, 12, and then if you get close up to the top, well, 400 is divisible by 4, but we're not including 400, so 4 before that, right? This would go up to 396. Okay, and looking at that, it might not be clear how many there are, but if you do the same exact trick that we just did, you could rewrite each of these as, you know what, let me stack them so it's a little easier to see this. You see that I could write this as 4 times 1, 4 times 2, 4 times 3, and so on. And now that I have this pattern, you see it's really easy to count them. As long, you know, I mean, you have to figure this out is 3 times 99. And now it's pretty clear that there's 99 of them in there. Okay? Okay, so there's 99 of them that are divisible by 4. Okay, do the same trick for 6. Maybe we'll call that S for 6. Okay, so it'd be 6, 12, 18, and so on. And 396 is actually divisible by 6 because it's divisible by 2 and 3, right? So 15, yeah. Okay, so 396. And you can write this as 6 times 1, 6 times 2, 6 times 3, all the way up to 396, which is 6 times 66. So there are 66 numbers in that set. Okay, and are divisible by 4 or 5. So do you see that because of this work here, if you want to figure out how many are divisible by 4 or 5, that's a union, right? So I've already figured out, so how many would that be? That would be the size of the union of F and S, right? Because F was the set of things that are in this original universe that are divisible by 4. S was divisible by 6. So you're figuring out this union now. Okay, so this would be, using the inclusion-exclusion, would be the size of F plus the size of S minus the size of this intersection. Okay, now I know these two, we just figured those out, right? So the size of F was 99, the size of S was 66, but I still have to figure out this. Okay, so let's explore that a little bit. Well, F intersect S would be the set of things in your universe that are divisible by 4 and 6, right? So X is divisible by 4 and also 6, right? So you could write that two different ways. You could say 4 divides X. First, let me write it like this, actually. So X is in F and X is in S. Okay, so what does that mean? Well, it has to be divisible by 4. So 4 divides X, and it has to be divisible by 6. So 6 divides X, right? So that actually gives you two equations. You actually know that X is equal to 4J for some J, and X has to be equal to 6L for some integer L. Okay, now these two together, if you stare at this a little bit, you see that this is 2 times 2J, and this is 2 times 3L. Okay, now if I have to satisfy both of these equations, then one way that you could rewrite this is X is what? It's actually got to be of the form 2 times 2 times 3 times an integer, right? This will guarantee that it's divisible by 4, and then the second condition, divisible by 6. Really what you're actually computing here is the least common multiple of 4 and 6, right? Because this is actually 12, right, if you actually compute this. And that right there is the least common multiple of 4 and 6, right? Because you got to ensure that whatever this number is, it's got to be divisible by 4 and it's got to be divisible by 6, okay? So where q is an integer. So really you're just looking at multiples of 12 here. So multiples of 12. And how many of those are there? Well, if you just list this out, so that would be 12, 24, 36, all the way up to 396. Okay, and you do our trick again. This would be 12 times 1, 12 times 2, all the way up to 12 times 33. Okay, so the size of this intersection is 33. And now you can compute what this union is, right? So thus, the size of that union is 99 plus 66 minus, right? And come back up here, subtract this 33, and you get 66, right? Because it's just 30, it's just, oh, sorry, no, you add them and then subtract this. So 132. Sorry about that. I had to think about it a little bit. Oop, I don't think it. Oh, you know what? I just realized that this got cut off too. So this is multiples of 12. I wrote it over here, but the screen edge got cut off. And then this, whoops, so that's 12. And this is 132, right? So 132. Okay, so that fits. Okay. Okay. So they are divisible by 4, but not 6. Okay, well, if you kind of think about that, you're trying to calculate the size of the relative difference, right? So it would be as if you have your set F and your set S, okay, and you're trying to take this out, right? Actually, let me write it like this. So remember, this red set would be F relative difference, right? So you're going to take out what's over here, and what's in this portion, that's the intersection, right? So what you're actually doing there, so the green is the intersection, but do you see you want to figure out how big this set is? Okay, so this is your red set. You want to know how big that is. Well, that would be the size of F minus the size of this intersection. Sorry, I'm switching colors again. So it'd be the size of F, and then you would subtract off the size of the intersection. And that's your green set there. But we've already figured out this, right? So that intersection was multiples of 12, and we knew how many those were, and we know how big F is. So we actually can tell how big this set is. Okay. So again, these will be multiples of 4 that are not multiples of 6, and that would be exactly here, right? So there was 99 of these, and there were 33 of these, so there are exactly 66 multiples of 4 in the original universe, right? The original universe is not all integers, it's the positive ones that are less than 400, right? So there are 66 total that are in F. So they're divisible by 4, but they're not divisible by 6. Now, keep in mind, I have to subtract off this intersection. I'm not going to subtract off all of S. You see, that would be too much. If I subtracted all of S, then I would be taking out this number. I would be taking out things that don't even belong to this intersection. So that's why that wouldn't be the correct thing to do. Okay, and that's definitely a non-trivial problem. But I wanted you to see this inclusion-exclusion principle used again in a more enumerative way, right? Calculating and counting things that are definitely non-trivial. So now when I say that there's a whole area of math devoted to counting, you can see that it's things can be extraordinarily complicated to count, all right? And that's why there is a whole area of mathematics devoted to this, called enumerative combinatorics. Combinatorics itself is quite a large field. Discrete math is usually considered a portion of, or combinatorics is a part of discrete math. So we will pick up with this next time, and we'll introduce other interesting ways to look at enumerative combinatorics and some of these related problems.